Hey, hello, welcome to the channel. Today we are going to discuss about multi-layer backpropagation. In the last video, I explained about single-layer backpropagation, and that is pretty much the chain rule. Once you understand the chain rule, the single backpropagation is easy. But here we are doing something with multi-layered propagation. So if I try to explain it in deep, it will become a math class, but here we don't have the privilege of time. So basically I'll go through the initial concept. So here what I have is the single gradient, I mean chain rule, single chain rule of the back propagation we have discussed in the last video, where dl is the loss, w is the weight, z is the sum of the loss, I mean sum of the activation functions, y is the predicted values. So basically we are just dividing dl dw into three dependent values, or three dependent derivatives. Here this is multi-layered, so there will be so many steps. The goal is the same, dl by dw1, but there will be multiple weights. Right now for this example we are only taking two layers, so let's try to simplify this a little as much as possible. So basically before going through the mess we are going to discuss, we need to know a few things. Basically the weights for a multi-layer network look like this. There will be output neurons, and there will be inputs. These are the weights that we'll have, and the model will have, I mean the feature matrix will only have inputs. So basically we can't do the same thing that we do for single propagation like this x w1 plus b. So what we have to do here is we have to take the x with the w1, there will be w2 too, which is the output layer, and w1 is the hidden layer. And what we have to do is basically we can't do anything that are in different dimensions like this. Here we have input, and the first thing that this thing starts with this output neurons and the input. So what we have to do is we need to take the transpose of it. That means we need to reverse their rows to columns. So that will be x into wt1 plus transpose plus b. So this is the very first step, and the same thing we did. And using this, we'll calculate the value dl by, I mean dl by dy. But to calculate dl by dy, we need to calculate the initial dl d2, and I mean dl z2 and dl dz2 by da1. So basically, these are just the same equation in different places. And what our formula does is, first it will compute this, and the result will compute the this value, and using that result we'll compute this. We'll have a ReLU gate in between so that we don't encounter the dead neuron problem. So let's say I sent a negative value to the next neuron, and the model will break. So we'll have a ReLU gate here. This is another additional layer we have. Okay, enough with the chat. And we also do one step here. We'll make a, basically this these values we got, these will be in 1D, and but the other values will be in 2D. So to make this possible, we'll convert this to 2D, and once we got the result we'll convert it back to 1D. So it's just an intermediate step in between. So these are the basics you need to remember. There is also one thing called Jacobians, that is in 10th math, I think. So what Jacobian does in simple words without using any formulas, let's say you have two functions, f of x comma y, basically a function with two arguments, and another function g of x comma y. So using these, I mean with these two, we need a single value so that we'll end up with a single truth. So for this we'll have a matrix, and in that we'll take the partial derivatives of each. That will be dou f x, dou y, and dou g by dou x, dou y, and basically what we'll do is we'll multiply these two and these two. The we'll subtract these two. The first diagonal, we'll subtract this. I mean we'll multiply this, and no, we subtract this, and we'll multiply with the subtraction of this. So that will be the Jacobian formula, and that is another step here. So basically, that's the thing that will give us a value at the end. So let's quickly go through the code. Once I go through the code, I'll explain each step we have here so that it will be easy to understand what each step does, and we'll have a clear value. For this, we need help of the solution because I can't remember everything. Why I'm not remembering here is because we all this backward propagation we are doing is just a single function in the newer libraries that are introduced. So basically this is just for practice. So initially we'll have the first value, that will be, and this at the rate is matrix multiplication. We did the dot product, right? Np dot dot. This is the simpler way in modern Python, and T is the transpose, and this is the bias b1. And what we'll do is we'll apply the activation function just like forward pass, and we'll calculate the ReLU of this. And there will be another. This is the hidden layer, so we need to apply this to the predictions too. So this is the real output we'll get, z2. A1 is the hidden layer value, and we'll take the w2. So that's the weight 2, and this is the transpose again, and we'll have a bias 2 for this. And in the end, we'll just calculate the loss, that will be np dot mean. So that's pretty much simple, y minus y true whole square. So we'll take the predicted value. We know that we need to take the predicted value first so that we don't encounter any dead neurons. I mean, there is no dead values. So this is the forward pass, and here's the main problem: the backward pass. In modern libraries, it is quite simple. We'll just call it loss dot backward, maybe something similar to that. And what we'll do is we'll take the length of the y we got. I mean the length of the true value, and if y true dimensions is greater than 0, else 1, so that we can maintain a positive value of the n number of neurons. And we'll calculate the dz2. So this is basically dl by dz2. So this is the first thing, dl by dz2, and we'll calculating this first. This is the first part of the backward pass. I mean the first determinant. I mean the first derivative. This is pretty much similar to the derivative of the mean will do like what's x square derivative, that is 2x. This is the same thing we are doing here, and this will be dw2. That will be the dl by dw2. So that's an intermediate step to calculate the dl by da1. And for now, let's copy this because I'm little bored. So basically, this does the same thing we do in matrix multiplication. And dz2 is a single array 1D. So using this minus 1 and comma 1, I made them 2D so that I can multiply with the a1 value. A1 is this, the maximum we got. And let's take the bias as dz2. I'll explain each of the uh, individually. And here we'll have da1. So let's copy this one because we are doing the same step again and again. The multiplication, here we did the multiplication, here we did the multiplication, here we did the multiplication, all of that in a multiplication fashion. But we just need to remember the values. This flattening is for getting the last value we need. I mean, we have already discussed one step. From 2D we need to make it 1D again. And we'll apply the ReLU mask so that it will be easy for calculations. And no negative values are escaping the output. So this is pretty straightforward. We'll just take the z1 greater than 0. And just like the last step we did, dz2 reshape, a1 reshape, this will be x. I know this is pretty much ugly, the code, but all of this we can uncover. I have something to show. Again, we'll take the db1. This is backward pass, so that's why we calculated db2 first and came back to db1. That's the backward pass. And end of the day, we'll just return these things, dw1 db1. After that, we'll calculate the gradient in the end. And let's just run it. And there is still errors here, and we don't know why. I should have stick to copy pasting all this. I don't know what the error is. So t has no attributes. Do I need to import something? No. Any idea why? Let's copy this thing. I don't know where I did this wrong. There is still something wrong here. I can't make sense out of it. Okay, then let's copy paste this thing. I think we are done. Let me go through the explanation. I don't think even if I try, I can remember this thing. So let's explain each step so that it will be easy for everyone, for me, and who are watching this. So in the layer one, we calculate the linear combination. That will be the very first thing we'll do. This is for the forward pass, and we'll take the loss function, I mean activation function. After that, we'll do pre-activation again for the layer two, because we are taking two layers here. And after that, Normally we'll just calculate the loss, and this is the backward pass. That means we are going back to the layer 1 again just to get some knack of it. And here I updated the w1 with the values I got from the loss. And after that, I'll reshape the dz2, and dz2 is basically the activation values we got. This is the dz2 of this value. We are coming backwards, so that will be dz2 first. After that, we'll be going to da1, and from that we'll going to dz1. So the order is simple. Initially I'll calculate the z1, and go to a1 and go to z2, and I'll calculate the loss. I'll come back, update the weight value 1, and after that, I'll I'll be going backwards. That will be, I'll take the dz2 first, and after that I'll go to da1, and after that I'll go to dz1. So this is the way we are going through, and after that we'll multiply based on the matrix multiplication. So basically we'll do the first step again in different cases. I'll add this links and everything that is required, the Jacobian principles, in the description. It is quite tricky, but when you get the knack of it, it is quite easy. And this is needed to understand the further concepts like multi-layered perceptron. Then there are so many stuff. So this is the basic foundation. This is as far as I can understand. So whoever's watching it, thanks for watching. I know I'm a little rustic today, but I think I understand at least a little bit of this. So thanks for watching. Please like, share, and subscribe. And I'll add the problem link and descriptions to read this. Quite tricky, quite hard to understand in a single video, but this is the gist of it. Go through loop, and go back again, compute different values, and here we have multiple values, so it includes matrix multiplications. So this is all about it. Thanks for watching. Please like, share, and subscribe.